Okay, Assalamualaikum, hi, and welcome back to Instrumentation and Measurement, Chapter 7 on sensors and transducers. So we talked about previously on strain gauges, what is a strain and what is strain gauges, and now let's talk about what is the working principle of strain gauge. Okay, before that, let me discuss to you a few practical applications of strain gauge. Some of you might wonder where it's being used and why it matters to engineering. So basically, strain gauges is mainly used for monitoring structures or monitoring objects that is being installed. For example, bridges, pipelines, buildings. Even if you look at some of these pictures here, see this is a strain gauge. Right? Which is installed on one of the beam of steel structure of a bridge. Need to monitor the movement, whether there is a compression or tensile whatever force going to that bridge. So it's very important for the engineer, civil engineer, mechanical engineer to know how much stress or how much strain is being exposed to all these beam and structures, so that it will not damage the equipment. The structure. And then, for example, this one is on the pipeline. Okay, this is installed on the pipeline because pipelines normally installed underground, sometimes or on the ground. So maybe movement of the earth, movement of the soil can also affect the pipeline. If we move too much, if we exposed to movement, very high movement, then it might damage the pipe and so on. Okay, so in R&D applications, R&D is research and development. In automotive, aerospace, oil and gas, power generation, geology, and so on and so forth. So basically, in a nutshell, that virtually in any sector of industry which require monitoring of object movement due to external force. So strain gauge is one of the better options for engineers and scientists to determine how much strain is being exposed to any of the object that they want to monitor, and it's very critical for them to understand, to use this transducer. So basically, let's talk about working principle. Okay, we know that the resistance of any conductor is directly proportional to its length and inversely proportional to its area of cross section. If you previously referred to your circuit analysis subject, R, which is resistance in ohm, units ohm, is equal to the resistivity multiplied by the length of the conductor divided by the cross-sectional area of a conductor. Okay, so where R is the wire of foil resistance. In this case, the conductor is the foil or the wire inside the strain gauge here. Okay, this is the wire here, and it has a certain resistivity, total resistivity between one and these leads. Okay, so it depends on the resistivity. The foil depends on the material of the conductor inside the strain gauge, and the length, the foil or the wire length, depends on the what type of strain gauge, right? And the cross-sectional area of the wire or foil. Okay, if it's a wire, maybe it looks like this. Okay, if it's a foil, maybe it's more like a square, something like that. So okay. All right, so we can deduce that if you look at these two formula, you can see that for tensile strength, if you look at tensile strength, tensile means when the force is acting this way, it's trying to pull, to elongate, to make the object longer, because this strain gauge is attached to a certain body or object, right? So when the object gets longer, or the object are exposed to force or tension, then the strain gauge will also expose to the same force. Okay, so as you can see, for tensile strain, you can see that the length of the foil, length of the strain gauge will get higher. Okay, and if you try to imagine yourself pulling something like a metal, when it gets longer, then the cross sectional for the same amount or a body of strain gauge or wire, the cross-sectional area will reduce. Okay, all right, the cross-sectional area will reduce, and then in effect, if you reduce the cross-sectional area, if you increase the length, and then your resistivity will increase. Okay, for compression strain, okay, when compression strain means that the force is pushing the strain gauge this way, trying to compress the strain gauge. So you can see that what will happen is that the length of the strain gauge or the length of the foil or wire will reduce. And if we try to compress something like a rubber or something, the cross-sectional area will increase. Okay, the cross-sectional increase, and this will cause the resistance will decrease. Okay, so that is very important. So this kind of phenomena is called a piezoresistive effect. Okay, piezoresistive meaning that the resistance of strain gauges will be dependent on the mechanical force which is acted upon to. Okay, so strain gauges are also known as piezoresistive gauge, just as the name. Okay, so because of that, we can deduce that there are two physical parameters of a strain gauge, which is that the dimension, and the parameter that we need to consider, okay, is the dimension. When the metal conductor is stretched or compressed, its dimension will change. As I said, so the length and the cross-sectional area will change. And the third parameter is the resistance, which is the resistance. Because of these two changes, the total resistance will also change. All right. So this is just to show you a graphical view of how the strain gauge will change. Depends on the compression. In this case, it's a tension. Okay. When let's say this is something like if you put a strain gauge on this book, okay, so imagine that this picture on the slide here is this book, okay. So if you put a strain gauge on top of this book, and if you let's say for example this book is bent this way, okay, so the strain gauge on the top will expose a tension, okay, it will try to pull apart. Whereas on the bottom, if you put a strain gauge on the bottom, it will try to compress. Okay, if I let's say for example the body is being exposed to a force which cause the body to move this way. Okay, so if you strain gauge on the top, it will try to compress. Okay, and we have lower resistance. Okay, and so on. All right, so okay, a fundamental parameter of a strain gauge is what you call a gauge factor. Every strain gauge has this what you call gauge factor, or we call it K factor, not K-pop. It's a K factor, not Korean factor. It's what you call K. I'm not sure why, but it's a gauge factor. So it's also known as the sensitivity of the strain gauge, and it is defined or calculated as the ratio of the fractional change in electrical resistance to the fractional change in the length. Okay, so basically gauge factor, okay, it's the ratio of the change of resistance, which is delta R. It's the change of resistance divided by the original resistance divided by the change in length divided by the original length. Okay, so as we have seen before, change of length divided by original length is equal to strain. Okay, so we can also write the gauge factor in this way. All right, so this is just the meaning of each of the parameter for the formula. Delta R is the change of resistance, and R is the initial resistance, delta L the change of length, and L is the initial length, and the strain is delta L over L, which is strain. Okay, got that? Okay, let's take a look at a few examples here. Okay, so let's imagine there's a strain gauge with a factor of 2, a gauge factor of 2, this is GF, cemented to a steel bar, which is cemented means that it's glued to the steel bar, which is subjected to a strain of 1 times 10 to the minus 6, which is okay, the 10 to the minus 6, 10 micro strain. If the original resistance value of the gauge is 130 ohm, calculate the change in resistance. Okay, so remember the formula to solve this. You need to use the formula for the gauge factor, K or equals to GF. It's delta R over R divided by the now you are given the value of a strain is 1 times 60 is the value of E. Okay, if you rearrange the formula, you can back calculate the delta R is equal to K multiplied by E multiplied by R. This is not actually, it's epsilon, the strain, and you crunch in the number and you get the delta R is very, very small resistance. It's 260 micro ohm, very, very small resistance. Okay, So, you know, our normal multimeter cannot measure this very, very small change in resistance. So that a regular multimeter cannot be used to do this. So this can be solved by using a balanced Wheatstone bridge, in which case I will give to you a very short video to explain this application of strain gauge using Wheatstone bridge. Okay. Okay, let's take a look at another example. Okay. The unstressed resistance of a strain gauge is 350 ohm. Unstressed means that the original resistance without any stress being applied is 150 ohm, and its gauge factor is 2. So the question asks you to calculate the change in resistance if a strain E 0.0001 is applied to the strain gauge. Okay. Okay, just a few notes here that 350 ohm resistance is a typical value for a strain gauge, and E 0.001 is also a typical strain level for metallic objects. 0.001, I'm not so familiar with how to change it to mechanical value, but it actually corresponds to approximately 7 megapascal or 1000 psi in aluminum, or about 20 megapascal or 3000 psi in steel. So if you are studying mechanical engineering or maybe on dynamic systems, something like that, so you can go and check this this value here. Okay, so the solution is, again, if you we use again the formula for the gauge factor is theta R divided by R divided by theta L divided by L. Okay, so we know since the strain is given here, so you can use this part of the formula. So if you arrange that, you can still calculate it's the same formula as before. So theta R is equal to R multiplied by gauge factor multiplied by the strain, and you got this answer here, 0.07 ohm, very, very small ohm, 670 milliohm. Okay, so this change is very, it's very small, just 0.02% of the gauge total resistance, and it's very extremely small and require highly sensitive and expensive ohmmeter to measure. So the solution is using a Wheatstone bridge. Okay, so before you move on to a capacitive transducer, let me show you one example of on the shelf or typical price of a strain gauge that you can find and you can buy it. This is from RS electronic catalog in Malaysia. For this one, for the gauge length of 5 millimeter, a gauge factor of 2.1, gauge resistance of 120 ohm, you can buy it for around like 55 ringgit. It is a very okay, not that cheap, it's very small. See, it's around 5 millimeters, very, 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 very short. Okay, so you can get it for this price if you want to do it for your project and for your future PSM, final project, and so on. Okay, so I think that's all about I want to say about the working principle of strain gauge. We'll meet again in our next chapter, next topic on transducer. I'll see you again. So stay tuned and thank you very much. Have a good night. Assalamu alaikum.